So prior to this, we've talked about basically given a sample of COVID-19 sequences, we've talked about how can we, map those reads to the reference genome. We've talked about, how can we call the consensus sequence from those samples and get a genome sequence for this specific person's virus. And we even most recently talked about if you gave me a bunch of consensus sequences. So for example, if I gave you the 5,000 sequences that we just posted, how would you come up with some inferences about the relationships between those sequences? So last time we talked about multiple sequence alignment, which is just how can I get these sequences to line up so I can determine homology. I can figure out what letters of each of these genomes correspond to the same ancestral letter. So that was the focus of last time. So now today, our interests are in how do we actually infer a viral phylogeny? So how do I estimate the evolutionary history of these viruses? So here's the general outline for today. First, I'm just going to real quickly refresh your memory about how we think about mutations going along a phylogeny. And then the middle of the lecture, we're going to talk all about how we do modeling of nucleotide evolution. So before I introduce that, I'm going to talk about what's called a continuous time Markov chain, which is how it's kind of like the framework, the mathematical framework we use to be able to think of the models of evolution. And then I'm going to talk about the specific models. And lastly, I'm going to talk about how we use all of this information together to actually do phylogenetic inference. So as always, if you have any questions, please feel free to put them in the chat. I'm happy to help out. Okay, so let's refresh our memory. Mutations along a phylogeny. So remember, imagine I have some hypothetical evolutionary history, and I have some ancestral sequence at the root. So this is the common ancestor had the sequence ACGA. And remember, the root of the tree is back in time, and then going down the tree is forward in time, where leaves are present day. So imagine as I'm going forward in time, maybe this G here mutated into a C, and maybe going forward in time, this G here was deleted, and then forward in time here, maybe no other mutations happened. So this leaf, the sequence is ACCT. It's only accrued this one mutation. Maybe this leaf also had a C, like maybe this A here mutated to a C. So this sequence is these two mutations, so CCCT. Then this sequence, maybe no other mutations happen, so it only has this deletion. And then maybe here, this C mutated to a G down this branch. And remember, we actually don't have access to the evolutionary tree. That's the motivation of today. How do we actually figure it out? And also remember, we don't have direct access to the gaps. So fortunately for us, if we just leverage what we talked about last time, we can figure out how to plug those gaps back in. We can just run multiple sequence alignment, and it might not be perfect, but we can try to stick those gaps back in as best we can. So today's focus is, okay, given this multiple sequence alignment, so given all of the sequences lined up perfectly, how do I actually estimate the evolutionary history? Okay, so that's kind of the context. Let's first talk about continuous time Markov chains. And this is going to be the framework around which any modeling that we do is going to be centered. So first, what is a Markov chain? So a Markov chain is a weighted graph. If you've taken a CS class, you might have heard the term graph, but a graph is just a network. So a Markov chain is just a network where the connections between any given nodes in this network have some weight associated with them, some value. So the nodes in a Markov chain represent states, states that I could theoretically be in. And the edges, they represent transitions between states. So they're directed edges. I can go from one state to another state. And they have some weight, which represents the probability of transition. So if I'm in one state currently, the transition from this state to another one has some probability associated with it. So here's just an example that we could use to represent the weather in San Diego as a Markov chain. So here I have 3 states, sunny, cloudy, and rainy. And the edges of this network represent transitions between states. So I can go from sunny to cloudy. I can go from sunny to sunny. So maybe today is sunny, tomorrow is also sunny. Maybe I can go today is sunny, but tomorrow is rainy. I can transition between any given pair of states. And further, each of those transitions has some probability. So if today is sunny, there's a 70% chance that tomorrow is going to be sunny. There's a 20% chance that tomorrow is going to be cloudy. And then there's a 10% chance tomorrow is going to be rainy. So that's all a Markov chain is, just a bunch of states with all of their possible transitions with weights on them, probabilities. Any questions so far? Kind of makes sense? Okay. So why is it a Markov chain? What does Markov actually mean? So there's what's called the Markov property, which is basically, it's saying that Markov chains are what is called memoryless. So what does memoryless mean? It means that, so first I'm going to give you a mathematical definition. It means that the probability that the state that I'm in at time I+1 is some specific state, given that the state that I was in at time I was some specific state that I was in, all the way down to the state that I was at time 0 was whatever specific state I happened to be in. This probability, so the probability of my next state being something specific, given all of my previous states, equals just the probability of my next state being a specific state, given my current state, right? Given my current state is something specific. This is a lot of math. Don't worry about it. In English, all that means is where I go next only depends on where I currently am, right? So if I'm currently sunny, the probability that tomorrow is rainy or cloudy or sunny only depends on the fact that today is sunny. It doesn't depend on the fact that yesterday was sunny or the day before was rainy or anything. None of the previous days matter. To determine what is the probability of where I am tomorrow, the only thing that matters is where I am today. Does that kind of make sense? So this is why it's called memoryless. We don't care about anything that happened in the past. All right, seems like that makes sense. Okay, so how do we define a Markov chain? What are the aspects? What are the properties of a Markov chain? Well, first I have to define the states. So in the previous example that I used, the weather one, my states are sunny, cloudy, and rainy. And I'm just going to call the state of, the set of states, I'm going to call it S. S is a set containing 3 states, sunny, cloudy, and rainy. Okay, so in addition to my states, I have to have initial state probabilities. So my Markov chain, I'm going to use it to describe some observed window of time. What was the probability that the first day in my window of time happened to be sunny or happened to be cloudy or happened to be rainy? What's the probability that the first day is in any of these 3 states? So let's pretend that the probability that the first day is sunny is 0.7. The probability that the first day is cloudy is 0.2. And the probability that the first day is rainy is 0.1. So just what is the probability that the very first day that I'm starting to check is in any of the given states? Okay, and then the last thing is the transition matrix, right? I have to define the transitions from each state to each state. And I can represent this using a matrix. So here I have a matrix that's 3 by 3. It's number of states by number of states, where here each row denotes where I'm coming from and each column denotes where I'm going to. So the transition probability from sunny to sunny, so the probability that today is sunny and then tomorrow is also sunny, is 0.7, versus the probability of going from sunny to cloudy is 0.2, probability of going from sunny to rainy is 0.1, etc. And you'll notice that every single row adds up to 1. And this is necessary because if today is sunny, tomorrow has to either be sunny, cloudy, or rainy. The sum of all of those outgoing probabilities has to be 100% because I have to go somewhere. Does that kind of make sense? So every row of this matrix needs to add up to 1. Any questions so far? Feel free to interject if you have any concerns. No, still making sense? Okay. Okay, so we talked about the simple weather example and how I can define a Markov chain in that weather example. And I've defined probabilities of going from one weather to another weather state from today to tomorrow. So every day I jump between weather states. So what exactly is a continuous time Markov chain? So in the previous example, time was discrete. I said today is sunny, tomorrow is rainy, the next day is cloudy. Weather changed in discrete daily chunks. And discrete, by the way, in math sense, if you're not familiar with that term, discrete just means integers. It just means, you know, we don't have continuous values. We only have fixed integer values. But in reality, weather doesn't work like that, right? It's not like it's sunny from 12 a.m. until 11:59 p.m. and then all of a sudden the next day at midnight it's rainy all day, and then the next day, right? Weather is continuous time. It changes continuously throughout the day. It's not bound by discrete day-by-day constraints, right? So maybe it's sunny, but then as the day's going on, clouds slowly come in, and then eventually it starts to rain, and then maybe it stops raining. These are continuous time events. So this is precisely a continuous time Markov chain. It's just the same exact Markov chain we just talked about, but instead of defining time to be discrete jumps, time is continuous. You continuously move across the states, right? So instead of jumping from states, you're just continuously moving across the states. Any questions about what that means? I feel like this is a kind of abstract concept. So if you're confused at all, please feel free to ask in the chat. Okay, so yeah, so instead of discrete time steps, today, tomorrow, day after tomorrow, time is continuous. So how does that change how we define the Markov chain? Well, a probability is an event. It's right. If I have a probability of like flipping a coin and getting heads, I flip a coin. Like I have to do a discrete event to get a probability. But in this continuous time transitioning between states, the notion of a probability doesn't really make sense because we're not jumping from somewhere with some probability. Instead, we use the term transition rate. So it's a continuous time rate. Kind of think of it like flowing between states. What is, you know, given that I'm currently sunny, you know, how, like, what is the rate at which I stay sunny versus transition to cloudy versus transition to rainy? So it's like, just if you think of probability, but as a continuous time phenomenon, that would be like a rate. And if this stuff's confusing, don't worry too much about it. This is like kind of upper division math related concepts. So I just want to briefly introduce everyone to these at a very high level. Okay, so any questions about either Markov chains or continuous time Markov chains? Basically, I have states. I have probabilities of being in any given state at the very beginning. And I have transitions, whether those transitions are probabilities for discrete time or rates for continuous time. You know, questions kind of make sense? Okay. So how do we actually use this? I introduced this complicated math concept of a continuous time Markov chain. How do I use it to model nucleotide evolution? Well, if you think about it, in my previous example, whether was sunny, rainy, or cloudy, if you think about the evolution of a single nucleotide, a single letter in the genome, you can think of it as weather, where the weather is either A, C, G, or T. So this letter starts at one of those letters in the ancestor way back when, and then over time, it continuously has some rate of changing from from whatever letter it was to either A, C, G, or T. Like it'll either stay the same or change to one of the other three letters. So it's exactly like the weather example, just instead of weather changing over time, it's a letter changing over time, but exactly the same thing. Is that connection clear? Do people follow what I mean by like states in this content, or like in this context? Makes sense. Okay, so yeah, same exact thing as the weather example, except our weather are the letters A, C, G, and T instead of sunny, rainy, cloudy. And then the initial state probabilities, it's going to depend on the specific model, but it's basically what is the probability that my ancestor was A versus C versus G versus T. Okay, and then transition rates, again, this will depend on the specific model, but these are the rates of going from A to C, from A to G, from A to T, etc. And just like before, I can represent it using a matrix. It's not a probability matrix because these are not probabilities because it's continuous time, right? It's not discrete time. These are rates, but still I have a rate matrix that describes the rate of going from A to A to C, A to G, A to T, blah, blah, blah. Okay, so in practice, these models that we use to study nucleotide evolution, they are what are called time-reversible models. So the rate from A to C, we define it in the model as equal to the rate from C to A, right? So here I'm just saying the transition value from any letter X to letter Y is the same as the transition value from Y to X. So as far as parameters go, we only have to care about the top diagonal half of this matrix, right? If you told me A to C, that automatically tells me C to A. I don't have to define it twice. So the only free to change variables are these ones. And you might be wondering, why is this diagonal blacked out as well? Why is this not free to change? And if you think about it, just like with the probability example, I know that the sum of the probabilities of any given row of the probability matrix has to equal 1. So if you gave me all of the elements except for one of them, I could figure out what that one had to be based on the values of the other ones, right? So I don't know if people have learned the term degrees of freedom from like genetics or something like that. But in any given row, so like in this row, I only have 3 degrees of freedom. If you gave me these 3 values, I could use those plus what I know about the constraints of this to figure out this other value. Does that kind of make sense? So the bottom line, if that was a little bit confusing, the bottom line is that for any of the models of nucleotide evolution that I have to talk about, the only transitions that we have to figure out how to define are these 6. Every other transition, so all of these grayed out ones, we could figure out as long as you gave me these 6. How do we do it? You don't have to worry about it for now, but just know that it is possible. Okay, any questions? No. Okay, so it's a continuous time Markov chain. Our states are A, C, G, or T. My model needs to tell me what is the probability of starting in each of those states. My model also needs to tell me what are these 6 transition rates. Okay, so now we're going to jump right into some of the standard historical models of nucleotide evolution. So the very first model of nucleotide evolution, which is the simplest model, is called the Jukes-Cantor model that was published in 1969. So usually people say JC69 for Jukes-Cantor, 1969. And this model assumes that all of the base frequencies are the same So that initial probability matrix, all 4 values are just 1/4. And it assumes that all of my transition rates are equal. So it assumes every single one of these question marks is exactly the same. I'm equally likely of going A to C, A to G, A to T, like every mutation that's possible is identical. They're indistinguishable. Okay, so someone asked in the chat, can you clarify the concept of a transition rate again? So think of it as like transition probability. So like a probability of going from A, so like let's say I said you have a mutation that goes from A to C, or from A to G, or from A to T. A probability is like a fixed like value that a discrete event can have. But really, these models, so I'm just going to kind of quickly annotate on this slide. These models are basically evolving. So like let's say I have like this evolutionary tree here. I'm just going to zoom in on this branch, and let's pretend that my letter in one of the positions of my genome in the ancestor was an A. And I'm going to zoom in on this branch. So on that one branch, my ancestor had the letter A, and we can think of mutations as we can think of evolution as kind of like a continuous process. Like over time, this A is continuously potentially going to mutate to something else. So instead of having like discrete time steps, like today, tomorrow, the day after, like did the A mutate to a C tomorrow? Or did it mutate to a G? Or did it mutate to a T? Like maybe do I use days for these time steps of like maybe it turned into a C, then maybe it stayed as a C, maybe it stayed as a C again, maybe this time tomorrow it mutated to a G, so on. Do I use days to describe this? Probably not. That's too big of a time step. Do I use hours to define this? Again, too small. Do I use seconds? Do I use minutes, seconds, nanoseconds? The time step becomes infinitely smaller and smaller until it's like infinitely small time steps, in which case this is a continuous time process. So basically think of a transition rate as just the equivalent of a transition probability, but if I thought about it in continuous time. So my discrete time steps are infinitely small. Does that kind of make sense? It's a little bit abstract, but yeah, it's basically the continuous time equivalent of a probability. But probability is a discrete event that happens. Versus this, I'm making that discrete time infinitely small. Cool. Yeah, no problem. Yeah, great question. Okay, so the Jukes-Cantor model, this is the simplest model of evolution. Basically, all of the probabilities are equal. They're just all 1 out of 4. And all of the rates are equal. They're just whatever my rate of mutation is. But in reality, the biochemical properties of these different nucleotides, as well as the genetics properties of like, what do they code for? Like maybe this codon codes for one thing, maybe this other codon codes for something else. Mutations between different letters could have substantially different selection pressure or biochemical or biophysical properties that allow them. It's not a very realistic assumption to assume that all of these letters mutate equally freely. So in 1980, the author Kimura came up with the Kimura 1980 model, so K80, which just like the JC69 model, he assumes all of the starting probabilities are equal. They're all 1 out of 4. But now, instead of assuming every single transition is identical, this model distinguishes between transitions and transversions. So in the DNA alphabet, we have what are called purines and what are called pyrimidines. So purines are A and G, and pyrimidines are C and T. And you know, the categorization of them as purine versus pyrimidine, this has to do with their organic chemistry, like their chemical structure. But for the purposes of this, don't worry about it. Just know A and G are fairly chemically similar. C and T are fairly chemically similar. So what this model is doing, it's saying going from purine to purine, or going from pyrimidine to pyrimidine, so staying within your same class of nucleotide, is one type of event. These are called transitions. And these have equal rates, like this and this have the same rate, the rate of a transition. And transversions, so going from purine to pyrimidine, or going from pyrimidine to purine, these have a different rate. Right, so A to G and C to T, these are both purine to purine, pyrimidine to pyrimidine, these are both transitions. These two have an equal rate. These 4 transversions have a different rate, but these two are equal to each other. These 4 are equal to each other. Does that kind of make sense? So there's only 2 rates here. There's these 2 rates are equal, and then these 4 rates are equal as well. There's a green rate and a red rate. Okay. Okay, so now we're getting a little bit more complicated. We're differentiating between these and these. Okay, then in 1981, he further expanded on his model to make to differentiate between 3 types of events. So transitions, so purine to purine, pyrimidine to pyrimidine, we already talked about that. But then even among transversions, he differentiated between conserving weak strong properties, so A and T, like either A to T or T to A, or C to G to G to A, right? So these are conserving weak strong properties versus transversions that are conserving amino or keto properties. These two is a separate category. And so I myself, I have no idea what either of these terms mean. I don't know what a weak or a strong property is. I don't know what amino versus keto property is. And I honestly, I don't care from my perspective. But this model sees these biological properties and says there's reason to believe that I should separate it into these 3 categories. So for our purposes, this means that we have 3 rates now. We have this green rate, this red rate, and this orange rate. And for whatever reason that the biologist tells me these 3 types of things are substantially different from each other, I take it at face value. And as far as modeling goes, I have the green rate, the red rate, and the orange rate. Does that kind of make sense? Any questions so far? Are people kind of following? Okay. It's going to get a little bit more complicated. So in 1980, actually, so this way it actually went a little bit easier. So in 1981, completely independently, there's a guy, Felsenstein, who came up with his own model of nucleotide evolution that we now call the F81 for Felsenstein 1981 model. And just like the JC69 model, just like that first simplest model that we had, as far as transitions go, it assumes that they're all equal. There's just one overall rate of transition. And here when I mean transition, I mean like state to state. I don't mean the DNA like purine pyrimidine thing. I just mean like between states. So all the rates are equal, but here the base frequencies are allowed to vary. So before we just assumed all of these pi values were equal and they were all just 1 out of 4. But now these are 4 different parameters, or really it's 3 parameters, right? Once we know 3 of them, we can figure out the 4th one by doing 1 minus the sum of these 3. We only have 3 degrees of freedom. But either way, these are now free to vary. They don't all have to be 1 out of 4. But this was kept simple. Okay, so in 1985, these 3 people, Hasegawa, Kishino, and Yano, they came up with their own model that, just like the F81 model that I just showed you, allows you to vary those probabilities. And then just like the K80 model, it lets you differentiate between purine and pyrimidine versus purine to pyrimidine or pyrimidine to purine. So it lets you differentiate between these 2 types of events. So the Felsenstein one, all of these rates are equal. Here, just like the K80 model, we have this type of rate and we have this type of rate. Right, so this is kind of like the merging of the F81 and the K80 model. It's the K80 model, but now allowing you to vary these bases, like these base frequencies. Okay, and then in 1992, Tamura came up with this T92 model that this bottom part stays the same. We have these two types of rates, and it's forcing the probability of A to equal the probability of T, and it's forcing the probability of C to equal the probability of G, but these two things are able to change. So like this could be something, this could be something else, but A and T have to be equal, C and G have to be equal. Okay, and I'm almost done. I'm just throwing a bunch of models at you just because there's been a lot of like incremental advances in this field. But yeah, so the Tamura-Nei 1993 model, the TN93 model, this allows the base frequencies to change. So A, C, G, and T could all have different base probabilities. And it supports this, it distinguishes between these following events, between A and G, between C and T, and between any of the transversions. So this model, as far as rates go, has the green rate, the yellow rate, and this red rate. And for a lot of real-world molecular epidemiology tools, this is actually one of the popular models that's being used. I won't talk about why for now, but in a future lecture, I'm going to bring this one up again. This is kind of one of the big popular ones. Okay, and then lastly, I swear this is the last one. I just threw a bunch of information at you. The last one is the generalized time-reversible or GTR model, which this is the most generalized evolutionary model out of everything I talked about. Basically, all of those other ones were forcing some things to be equal, right? At least some pair of items was forced to be equal for all of the models I showed you before. This one is the most generalized. Every single one of these values, the probability of A, the probability of C, the probability of G, the probability of T, and all 6 of these rates are allowed to be whatever you want them to be. So this is ideally, this is the most generalized model people use. This is kind of, if you don't know what to do, this is the model that you want to pick. It makes the least assumptions. Any questions about that? So like the TLDR of all of this information is this is the model you usually want to use if you don't know anything, versus this is kind of like the second most popular model. It has some assumptions, but it also has some other nice properties that I won't talk about today, but in a future lecture I'll talk about. Okay. Okay, so I just threw a ton of information at you. Why did I do this? Why did I throw all of this nonsense about models of nucleotide evolution? And what does any of this have to do with trees? So let's just quickly return to our original problem. I have a multiple sequence alignment, and the tree that generated these sequences, right, the evolutionary history between these present day sequences is hidden from me. I can't see it. What I want to do is kind of, pull away the curtain. I want to see what was that evolutionary history. So let's formulate this as a computational problem. So let's imagine someone gave me a candidate tree. Someone said, you have these 4 sequences. Well, I personally think this tree is the tree that gave rise to them. This is the evolutionary history of them. How do we score this candidate tree? So some random person gives us a tree. How do I score how good or how bad this tree is? So first, what do we have at our disposal? We have our model of evolution, which let's assume that we've parameterized it. So let's assume we took any of those many models of evolution that I just described to you. Let's say the GTR model. And let's say we also have all of the parameters that we are able to pick. I'm going to call that combination theta. So this is our parameterized model of evolution. We have which model we want to use, as well as every single the nucleotide probabilities and all 6 of the rates. We have that at our disposal. Let's pretend that we have that. We also have the multiple sequence alignment, right? That was our input. We're trying to estimate the evolutionary history of our multiple sequence alignment. So we have the multiple sequence alignment at our disposal. And we have this specific candidate tree, this specific tree that someone gave to me and said, hey, I think this is the right evolutionary history. So how can I use this information to come up with some score of how good a tree is? Well, I can use my model of evolution to compute the probability of having observed these sequences given this specific tree that someone gave me and given my model parameters. So basically, under the assumptions made by the model of evolution that I've chosen, and given this tree, what is the probability that we evolved this specific set of sequences given those two things? So fortunately for us, this has been solved. So in 1973, Felsenstein, that name should hopefully sound familiar. There was the F81 model that we talked about. So Felsenstein came up with what's called the tree pruning algorithm, which for the purposes of this class, it's out of scope. If you're interested in it, once you've taken maybe CSE 101, like this is a dynamic programming algorithm that does a traversal of the tree in order to compute the global score. But for our purposes, let's not even worry about it. It exists. That's all I care. So I can basically take the tree, take the model parameters, take my sequences, and then run this Felsenstein's tree pruning algorithm, and out comes a score, or out comes the probability, which I could theoretically use as a score, right? Okay, so given some tree, how, so if you gave me some tree, I could compute the score of that tree. But I still haven't solved the problem. How do I actually find a tree, right? Someone gave me this candidate tree that I'm trying to score. But how do I come up with a tree from scratch? So this general problem is called maximum likelihood phylogenetic inference. Fancy name, but first of all, the phylogenetic inference part, phylogeny is just another word for evolutionary tree. Inference, we're inferring it. So this is just inferring an evolutionary tree using what's called maximum likelihood. So what does maximum likelihood mean? Okay, well, so first, just given my multiple sequence alignment, I can compute just a quick and dirty tree. So there's an algorithm called neighbor joining, where basically, assuming you have a bunch of items that you can compute pairwise distances from, the neighbor joining algorithm basically takes the smallest pairwise distance pair and merges them. And then it takes the next smallest pairwise distance pair and merges them, and just keeps merging pairs until eventually you only have one more item. And this tree structure is a tree that we can get. So for the purposes of this talk, don't worry about the nitty-gritty specifics of this algorithm, but just know there exists some algorithm that's relatively simple that I can just feed it my multiple sequence alignment, and using pairwise distances, it will generate a tree for me. It's not necessarily even remotely close to the true evolutionary tree, but it is a tree. Okay. So now what can I do? So I have a quick and dirty tree that I generated using this simple algorithm, but I want to improve it. So what I can do is, given this quick and dirty tree that I got, I can compute the likelihood score for that tree. I can compute the probability of observing those sequences given this specific tree that I got and given my model parameters, right? That was just Felsenstein's tree pruning algorithm. Okay, so now I have a quick and dirty tree and I have its likelihood score. What do I do now? Well, I can do what's called a tree search. I can basically make some small modification to the current tree. So maybe, maybe I just pick this branch, I just rip off this branch and just shove it somewhere else in the tree. I just make a small modification. Then this new tree that I get after ripping off this branch and sticking it here, just after doing some small modification, likewise, using the exact same algorithm, I can compute the score of this tree. And then what I can do is make a decision. If this new tree that I have has a better score than the previous tree that I had, I'm going to keep the new tree. And then I just keep repeating this process. So now, given this new tree that I have, let me again rip off one of the branches and stick it somewhere else, compute the likelihood score, check if that new one is better. And if it is, I'll keep the new tree. Or if it's worse, I'm going to throw away the new tree, stick with what I had. Repeat again. And I keep doing this over and over and over and over and over and over again until eventually, hopefully, I converge on a tree that has a maximum likelihood. It has the highest possible likelihood score, the score that I compute from Felsenstein's algorithm. Okay, so first of all, does that general approach make sense? In reality, there's a bunch of small details that make it a little bit more complicated, but this is kind of the overarching approach. Generate a quick dirty tree, and then just get the score of that tree and repeatedly make small modifications, get the new score. If it's better, keep it. And keep going, keep going, keep going, keep going until you no longer improve. Okay, so it seems like no one has questions. If you think of anything, feel free to type in the chat. Okay, so let's talk about the computational complexity of this. So this algorithm that I've described, it sounds interesting, but it sounds pretty slow. So in fact, this problem, the phylogenetic inference problem, is NP hard. So if you've taken a CS class, you might know what that term means, but for our purposes, all you should care about, if I say that a problem is NP hard, that just means that there does not exist an efficient exact solution. So just like multiple sequence alignment from last week, that was also an NP hard problem. There does not exist an efficient exact solution. So just like with multiple sequence alignment, what people do in practice is use what are called heuristics. We use algorithms that are not necessarily guaranteed to give me the absolute best answer, but we hope it usually will give us a fairly good answer. So in this context, let's assume n equals the number of sequences, k equals the length of each sequence, and a is the alphabet size. So for DNA sequences, A is 4. We have A, C, G, T. So the best heuristics, the fastest heuristics that are out there, as far as time complexity goes, they scale as big O of n to the 1.5 times log of n times Ka. And as far as space complexity goes, they scale n times k times A plus n to the 1.5. That's a bunch of math mumbo jumbo. If that doesn't make sense to you, don't even worry about it. The key takeaway is that, so for COVID-19, the length of my sequences is fixed. That's 29,000. Nothing I can do as a computer scientist can change that. That's just the biological length of a COVID-19 genome. And the size of the alphabet is 4, right? A, C, G, T. There's nothing I can do to change that. The only thing that changes with time is the number of sequences I have at my disposal. So really, K and A, for my purposes, I can think of as constants. And I'm interested in how does this scale as a function of n. And you'll see it scales almost quadratically as a function of n. So n to the 1.5 in space, n to the 1.5 times log of n in time. So not quite n squared. So it's not quite, if I double my input size, I quadruple my runtime. But it scales almost quadratically with the number of sequences. So not amazing, but this is the best we can do right now. Okay, so we're almost out of time. So just kind of to finish things off, I want to give you some brief overviews of the current state of the art tool. So again, like everything I'm discussing in this class, the end user doesn't have to worry about developing these methods from scratch. You're just going to take an existing tool that someone made and use it. So currently the most popular tool is called IQtree 2. So it's version 2 of IQtree. So generally this is considered as the best trade-off between accuracy and speed. So in general, for most heuristics, you can think, there's some trade-off between accuracy and speed. Usually if I go slower, I can get better accuracy. But if I lower my accuracy, I can improve my speed. So there's usually a trade-off. And this tool is generally regarded as the best trade-off. It gives you very, very accurate trees pretty reasonably fast. And if you go on Canvas, you can look at my slides. Here's the links to the website and the source code for this tool. So the fastest tool, but generally is considered the lower accuracy of the bunch, still decent accuracy, but not the best accuracy, is called FastTree2. And here is the link to have, so this is the link to the website, which also has the source code. I think IQtree is written in C++. I think FastTree is written just in straight up C. And then the slowest tool out of these ones, but generally the highest accuracy, is called RaxML-NG. And here's the website, and here's the source code. I think this one's written in C++. But yeah, in general, for me personally, I usually alternate between these two tools. I usually first try IQtree, and then if it's too slow, then I resort to using FastTree. But yeah, I encourage you, if you're curious at all about this, this is a very open problem that still no one really has a good answer to how to do it quickly. And yeah, it's just kind of a cool computational problem to work on. Okay, so I'm going to call it there. Thank you, everyone, for coming. If you have any questions, please feel free to reach out as always. Please don't forget to fill out those reflection surveys, just because I just want to know, like, how are you feeling about the materials? What did you particularly find interesting? And it gives me helpful feedback for improving this in the future. But yeah, thanks everyone for coming.